Welcome everyone to the One World Mind seminar.
NRT, One World Mind, you're gonna record it, I want to.
Yeah, NRT, One World Mind stock.
Yeah.
Very happy that we have, Edward Chou here, who will be starting at the University of, Pittsburgh, next fall, and is currently a postdoc, in Munich. Got his PhD from UCLA roughly 4 years ago. 4 years ago, yeah. See, and we'll be talking to us today about compressibility of neural networks. So looking forward to it. Take it away.
Okay. And first of all, thank you guys for the introduction and invitation. It's very nice to be here. All the sunshine and very good weather. Yeah, so today I will talk about theoretical guarantees of compressibility of neural network. And the key words here is implicit bias and neural collapse. So the talk, let's see. Okay, the talk will actually have two parts. So the goal is to establish some theory on neural network, especially on the training and how the initialization affects basically the limit. And so it is a complicated structure. And the way there are two approaches that I will present in this talk. One is bottom-up approach, meaning if you have a complicated thing, you reduce, you simplify as simple as possible, but not to the trivial case, and try to establish a theory on it, and you try to build from that. So that's the bottom-up approach, and that's through the implicit bias and regularization. So first of all, I will show you a very particular case where we can characterize why certain structure prefer certain kind of solution. Okay, and then it will become clear later on. But basically, the message is if you have a deep structure, then the solution you get will favor a sparse solution, which is not very trivial to derive. And then we generalize this particular system to a class of function, which we can derive similar result, but then it's no longer compressed sensing. It's more like it has a certain favor kind of metric, but this metric depends on your architecture, and everything is algebraically close. You can write down the equation, you compute it. And then we also care about not only characterize the limit, we also want to characterize the rate of convergence, because when you implement it, or if you run, the limit happens when time goes to infinity, but you don't have an infinite time. So you probably need to care about how can I do it in finite time. That's bottom-up approach. So the model will be simpler, but we have like complete theory. And the second part is from the top-down approach, meaning we literally look at a complex situation. And then, because the dynamic is very complicated, we cannot reduce to like single atom and analyze it, but we kind of analyze the whole thing as a whole, more like if you want to think about like statistical physics kind of approach. So you kind of have some information of the whole system. You don't have very good control of the individual characterization, but then you can derive some theory. So everything I present here are written up in paper with full proof, and if you find mistakes, be very, very happy to do that. Yes, and then I will suggest some future direction. If you want to discuss any of them. Okay, so maybe just one thing about why I think it's important to have some theoretical guarantee on machine learning, and actually. The problem is for safety, because we're trying to use machine learning algorithm into more and more delicate tasks. So initially, those online competition will classify dogs and cats or some image, and they say, oh, 95% accuracy, that's very good. Yeah, that is very good. But if you want to really implement it into some delicate tasks like self-driving, when you have 95% accuracy of classifying a car versus a pedestrian, not.
5% of dogs were classified as cats. We're not happy.
Not that can, but then no one's harm, right? I mean, well, unless you're adopting cats and dogs and online. Then okay,
This isn't a dog.
there will be some harm thing, but they're really pushing forward to this delicate task, not just self-driving like operation surgery, because machine has more stable kind of control. But what if they accidentally just kill the patients? So we really need safety, and we need accountability, because company will claim that they have 95% accuracy in certain tasks, but they do it empirically. And then if something goes wrong, they would just say, well, it happened. And this is, I personally think this is a bit dangerous if you really want to rely on it. So it will be very important if we can really set a bar saying that, yes, we know for sure this will work, at least under some condition. And I think explainability is also a big direction, but what I think is we teach machine to learn. And now machine learns something and we can actually learn from what they're learning, but in a way that human can understand. For example, like AlphaGo, now they learn how to play Go. They're doing moves that people don't make before. Now people actually analyze them and then they implement it to our ways. But this has to be the thing machine learning sometimes is very hard for human to digest to learn because it's very like it has a million parameters. And so you need to transform in a way that human can learn. And that's why I think it's very important because usually our brain is just very small and we can only digest very limited amount of information. So that's just a motivation. So that's part one, implicit bias and implicit regularization. This is a joint work with Johannes Fogger, Dominic, Rachel, Claudio from LMU, KU, so yeah, both in Munich and UT Austin and Harvard. So they're from those different places. And let's start with the open. No problem. It's very exciting, although there's no prize here. Then this is a very critical question, and I'm sure all of you have. And this still happened to me today too. The open question is, where should we go for lunch? And this is very you ask it every day, and when you have more people, when you have 10 people, you know the solution becomes the solutions may become very large. And the problem with this question is that, at least in my group, there's always a person who said he's good with everything, and when you propose a place, he will say he doesn't like it. Right? So in some sense, he's not explicitly biased towards anything, but he's implicitly biased. And let's think about, okay, how do we, suppose everyone is clear on their opinion, what do we usually make? How do we make a decision? So if you have 3 restaurants, here are the 2 categories, one's the price and one is the distance. First, usually what you have out of your option is you have a hard constraint. Basically, if you have $10 in your pocket, you eliminate B, right? There's a hard constraint, you can think about equality or inequality constraint. And then, but out of the 2, you still have more than one solution, and you have to choose one solution. So you need an extra metric to decide where you go. For example, well, you have limited number, and then you are lazy. This is very human nature kind of assumption. So this is how we make decision, and this is what a lot of optimization formulate. You have hard constraint, and you out of the thing that satisfy this constraint, you minimize some metric. Compressibility, you minimize one. Now, the thing is, machine also have this particular structure. So they try to minimize function, but there are infinite solutions on the loss function. But they always pick certain loss function, and we do not understand why they pick such. Is it because it's closest? Because it's cheap? Because it has a best curvature? We don't know, but we want to understand what is this implicit bias. Okay, so if we would take into like very easy, if you have linear regression, the blue line is the restaurant or the solution of your linear equation, you want to pick a solution. Right? So the classical thing will be, okay, do the projection, and this actually have a algebraic closed form. It's just the pseudo inverse solution. And or if you do compressors, you say -1. And for neural networks, basically we don't know, but it would be nice to know because then we know what kind of metric it's preferring to, and we kind of can predict if it converges, it has certain property. So we borrow something from conventional wisdom. So in optimization, so now we're talking about non-convex optimization. So landscape can be really crazy. Usually we don't have global result, but we have local results, saying that, okay, if you're already very close to a solution, then you might just fall. And this still happens when you do empirically, even on training a neural network. You tend to favor the solution closer to you than a solution that's very far. But the thing is, when we say close, that requires a measure. And the measure is not, it's not physical force, so it doesn't have to be completed, it doesn't have to be L2. And the question is, what is this metric? And I will show you a particular case where we can figure out this metric. And then there are ways to generalize such metric based on your architecture of optimization. So I know this word has been around in the literature for quite some time, and people use it with slightly different definition to their advantage of writing paper. This is the precise definition I got. It's the appropriate measure for closeness, so that if I plug it, I know my optimization problem. And for example, so basically implicit bias has to tie up with two things. One is the loss function you're doing, and one is the algorithm you're minimizing. Here we usually talk about gradient descent or gradient flow, meaning you just take your gradient and you just go down. Now, if you do linear regression, and forgive me for using W as variable and X, Y as data points, yeah, the convention for the computer science, I guess. If you just have this loss function and you do gradient descent to find a solution, you can calculate algebraically. And then it turns out the minimizer is a projection, basically, because you just want to go to the solution set as fast as possible. But what is funny is that we're trying to mimic the effect of deep structure. And deep structure meaning you just have a lot of layers. And at first we thought, well, adding a lot of layers actually doesn't help to represent a larger class function. Actually, you still have a linear regression. So why on earth would anyone, instead of having one variable vector, you have a lot of variable vector, but you're still doing linear regression? We did it anyway, to understand what happened. So here, W1 and WL, they're all vector of the same size, and the product is visualized. Okay, so we have this loss function, a lot of variables, and we just optimize them again to gradient descent and flow on each individual vector. But what we found out is if you actually compute it, will not minimize L2, will minimize L1. And this is very surprising. This is first come from empirical, just to experiment, because if this is the loss function, and I want you to tell me what's there, what kind of implicit bias you have. Wouldn't, I mean, for me at least, it wasn't clear. But you can prove it. And then, of course, there's a motivation for studying this model because we're thinking about neural network where you have bias, weight, and nonlinearity, and then we're like, okay, simplify things, no bias, simplify things, no nonlinearity, and then we go down to matrix. And then when we say matrix, and we further assume matrix have the same eigenspace, so it just only the eigenvalue matters, basically, and that's why it reduced to that case. So the first theorem of the talk. So if you have instead of one vector, if you have more than one vector, 2 or even more, like 10, 100,000. Once you go beyond 2 and you do you minimize the loss function through gradient flow. So when I say gradient flow, it's the infinitesimal analogy of gradient descent. You're doing a continuous and differential equation style except discrete. If we follow that, then first the limit exists, so they converge. And the second thing is that they converge very close to the minimum L1 solution, or the L1 norm is very close to minimum. In this case, there's a little bit of subtlety because you can only stay in the positive quadrant, but then we realize you double it. So someone take your positive, someone take your negative, you recover the sparse solution. Sorry, the minimum L1 solution. Yeah.
So W tilde of T, what's T when W tilde is a function of T? Is that the same as the superscript 1 to L?
So W tilde of T is just this. So W tilde of T is WL T automatic product with.
Oh, each of those W is a function of T.
Yeah.
And T is some parameterization of the gradient flow.
Yes. And
Okay.
throughout time, you kind of do the evolution, and you see this PD. Yeah. So you can write down the differential equation and analyze the limit, basically. But this is very surprising. And when I studied this, I didn't know this will go back to compressed sensing because I have no idea. I'm like, oh, it's a neural network. And it happened to be, oh, because of that one. It's very nice. I can show you a little simulation. One thing I want to mention is that it depends on your initialization. So if you have small error, a small initialization corresponds to small error. That's why in the literature, I think when they first discovered this phenomenon, they take the limit of initialization go to 0. Because then on the right-hand side, you have 0. Then you have exact L1 minimization. And this is consistent with the experiment. As initialization goes smaller, the reconstruction down. And it's also funny that the 2 layer is very different from 3, 4, 5, 6. So 2 and 3 seems to be a big threshold. And in analysis, you can also see in 2, you have some logarithm scaling. While you have when you have 3, 4, 5, 6, you have polynomial scale. There's a difference. And I want to emphasize this point because a lot of people are studying shallow neural network, which is only 2, and analogous with L is 2, and they believe that such analysis can carry through 3, 4, 5, 6, and more. But according to our experiment, there's a much difference actually. Yes, and small initialization means L1 minimizer, and if you have some RIP on your matrix, then you have solution. Yes, so that's the first thing. But this is just, again, this find you a sparse solution, but we know how to do compressors. So we consider other kind of class function, which we can do the same analysis. It turns out we can. So consider a more general model where loss function has 2 kinds of nonlinearity. One is outside and one is inside. And again, we're trying to optimize W through gradient descent of gradient flow. That again, we're trying to find the order state. In the one before, we have F1. Here we have the generalized version of that is the Bregman divergence. The Bregman divergence is a generalization of distance function. Basically, Bregman divergence is a distance function depends on the generated function f. So, for example, put as a square function, then you will get the Euclidean distance. If you put f as I think log or some or x log x, then you get the basically it's a distance function depends purely on the generating function. And how you derive this generating function is based on the nonlinearity of this rho RP stands for reparameterization. I didn't write the whole mechanics to derive it because it's algebraic basically. You take derivative, you do a U substitution, you take 1 over that, and you do twice integration, and you do a U substitution again, then you get your f. But it's purely algebraic close. That means if you give me a function and I know how to differentiate integrate that, I can do it. It might be ugly sometimes. So this is a very, I would say, quite general formulation. And this guarantees that we know what exactly the implicit is if you have such. And the goal, of course, is to stack this kind of analysis to more and more layers, and it will be interesting to see what are we implicit bias towards. I want to emphasize one thing is that usually the thing we add here are the metric we already know, like we want to know it's L2 or L1 because we know they have good property. But what if there are crazy polynomials here that we never thought of, but it's good? Maybe the machine has some good regularization thing that we don't know. So for example, you can play around. So if you read the paper, if your linearity satisfies the regular condition, you can put in any function you like. And you will output any kind of regularizer implicit bias thing. So we just plug in and play with it. Actually, for example, this function is this function that we never use as a regularizer. Actually, I didn't know it too much before. But it turns out this function, it looks like L2, so it's kind of differentiable, but it's L1 when you're far away from it. So it's a nice function, but I never thought about it. But I just plug in some known function and you play around and you realize, oh, if you mathematically calculate, this will be a regularizer.
So the TF is just a map from R and O. TF of Z, if you plug in a scalar. And
yeah,
it
no,
makes
Z
scalar.
is usually vector, so
Z is a
Z
vector,
is-
okay.
Yeah,
Point, well, okay.
this is,
Okay.
yeah.
Okay.
So, yeah, you can choose any nonlinearity, and then you can calculate the implicit bias. Well, whether it's useful or not depends on your application.
So what the Bregman divergence give you in actually in terms of compared to other like KL divergence?
So for example, KL divergence or let's say Euclidean distance is a particular app you already have in mind, right? And here the thing is,
It's not like what's the actual benefit you put everything into like the Bregman divergence. The framework what's the actual benefit are you in Bregman divergence in this setting?
the thing is I didn't put the Bregman divergence. I kind of understand if I have this loss function
Okay.
and I train it, what kind of limit it will go to, and I want to characterize it. So before, I don't even know what Bregman divergence is when I analyze this. And I analyzed the limit, I thought, oh, and through the analysis, you see that, oh, actually the limit satisfies certain optimization problem. And then this optimization problem can be written as it can also be written in other ways when you subtract some constant or that. But this gives you some sense of interpretation of what it means. So it doesn't have to be written as Bregman. Yeah. But also, so you can also do other way. If you have optimization problem in mind, you don't know how to solve it, but you know you can write it as a Bregman divergence with a quality constraint. Then you can say, okay, I can based on this, I reverse engineer, build a loss function like this, and I train based on this loss. Because when you have constraint optimization, usually what you have is you have a hyperparameter seeing the objective function and the constraint, like a plus lambda b, for example. And this lambda usually is something you took. You do experimentally, or you have some idea of how to scale. No, there is no hyperparameter. So this, I think this is a very, very interesting thing. You can relate constraint optimization. You can reduce the number of hyperparameter views here. Yes, so that's the characterization of the limit. But now I want to talk about convergence rate. So a lot of work, yeah.
So maybe I should ask my question now. So I just want to make sure I'm understanding. You're saying that, I could take I've got basically you're trying to understand these sort of projections, like if you're going to do an L2 projection onto a line. And you're saying that your training, that the training of your neural network looks like a certain type of projection.
Yes.
And this sort of Bregman projection or Bregman divergence is the limit of the infinitely deep neural network when it's being trained. Is that the right?
It doesn't have to be infinitely deep, actually.
It's infinite time then?
So no, this can be finite. This is basically, so for example.
So L is not going to infinity.
No. So everything I analyze in this whole talk, everything is finite. So for example, what we analyze in the beginning of the case, what you can think about is it's roughly polynomial. So instead of xw, I have xw to the L, kind of.
Yeah.
Like raised to the L power. And that's your nonlinearity. That's your row of RP. And if you tell me your row of RP is a polynomial function to the L, then I can tell you that if you converge, you will converge to minimum L1.
Yeah.
Now, if you tell me another thing, like you don't like polynomial, you like sine, then you have x sine w minus y, then you will have a different kind of bias. And then I'm just saying, maybe if we can work the other way around too. If I want to minimize L1, and I can write this right, I can go back and say, oh, if I minimize this L function, it will give me the same thing. This provides an alternative algorithm different from the conventional way to solve constraint optimization, which I think is quite good.
I see. Okay, you start, but you had T goes to infinity then.
Yeah, T goes to infinity.
And that is just completing the gradient descent
Yeah, the gradient
Until
descent,
it's
just
stable.
training. Yeah.
until it's there.
Until it's stable, yeah.
But somehow you need this in the proof, that this is something you need to understand that you have converged.
Yes, exactly. Yeah, you can prove convergence. In some other case, you have to assume.
Okay.
Yeah, so you have to. So if you have, yeah.
Okay, well, so what's on the sigma here?
Sigma?
Yeah.
This one? This is some motivation for like your network. Because this is like maybe ReLU or hypertension or something.
Then that function actually is a linear function. After you put y.
Yeah, this is a linear constraint. Yes, so the constraint needs certain linearity. Yeah, actually.
So that's not complete nonlinear neural net.
No, this is far away from the complete neural net. Like again, this is a bottom-down approach, so I try to reduce everything to the simplest case I can analyze, but it's non-trivial because this is all non-convex optimization, and basically I couldn't find on any text.
Okay.
I think this is a new chapter of optimization. I think it's fun. But then I also have to care about convergence rate because a lot of work when I start this, they're taking initialization 0 and they have to. And then I once had a master student say he will run the simulation. And then 2 days later, he told me that he doesn't believe the theory anymore. And I asked him why. And he showed me his plot. And his plot, the loss function is just flat. Nothing really changed. And I said, what did you do? He said, well, they said initialization as small as possible. So I take 10 to the negative 12. Like, okay, maybe you try 0.1 and then converge in 20 minutes. And then it's converging to the exact limit we want. And because there's a trade-off, I mean, the limit, when you write limit, something disappears, all the nasty terms disappear and look nice. But they really damage your convergence by a lot if you ever do experiment. So we were very concerned about that because I also like to do experiment to understand what's going on. So there are two solutions. They're corresponding to other paper. One is to use weight normalization, which is just reparameterize vector into polar coordinate. So unit vector times a magnitude. The second solution is to apply the natural acceleration, which is a well-known acceleration method for gradient descent. And both are, I'll say. So first, what we mean by weight normalization is really just okay, rewrite the polar coordinate and you optimize both variables disjointly, but at different rate. So here you optimize some, this one's slower, and the theorem tells us that again we have this arrow before. The arrow before only depends on the one norm of the initialization. Now, and we want the thing in the parentheses to be small, small arrow. Now the thing is now you have a row vector, and this row vector on the right scaling of the eta, the row is usually huge. The row is like 100. Okay? And if you have 100 to the -3, it's already very small. So to make everything small, if rho is huge, rho negative L is small, you don't need small initialization. And this, again, you can calculate explicitly, algebraically, and you can also see an experiment. So with normalization, it's the green and the red. And the blue and the orange are the ones I showed you before, like without normalization. You can see that the arrow all decrease when your initialization goes small, but the green and red decrease much, much faster. So you don't, for example, for the blue curve to have arrow 10 to the -6, you can think about have to extend way beyond this rule. So you might need initialization like 10 to the -6, which will slow down convergence. But with the green curve, you just need 10 to the -2, or even 10 to the -1 if you're okay with the loss in your arrow. So this helps a lot. And this is I mean, again, I test it out, and then I figure out, oh, when you write the differential equation, there's something invariant, and somehow there's exponential scaling in the vector, which is very nice. But let me show you another possible way to do it. Okay, this is another paper on archive which will update recently. So this is the most recent result. Please do not try to put it right after the talk. That's why I didn't show you all the details. So you cannot, you may not. So if t is the time of training you allow, then gradient method converge linearly. That means the loss decrease like 1/t. So we know it converges, but we didn't know what's the rate. Just here we can prove it's 1/t. And if you do natural acceleration on the model, you get 1/t squared. Decrease much faster. T squared. And notice this is natural doesn't necessarily have to work because all the natural theory based on convex optimization, actually it needs to be to some theory you need strongly convex. Our function, none of our functions are convex, but still works. We can prove that at least it has a theory. So there are two ways to accelerate this here. Okay, and here an experiment. If you have greater descent, your loss decrease in the blue. If you have natural, you have some oscillation, but it decreases much faster. Yeah. So, summary of the part one is that first, implicit bias or implicit regularization, if you want to think about, is the appropriate measure of distance. It's not L2, it doesn't have to be L1, it just depends on what kind of loss function you're training. You will have a different landscape. And the right metric, this function you should look at is the break. Yeah, divergence. And the convergence can be with normalization and natural, even though your loss function is not convex. It's not a problem, at least in our case. So I could not say for any cases, but there are cases we can show, and the thing is we want to extend such function classes. So if you remember, we start with an open question, right? So where should we go for lunch? And actually, I didn't have a perfect answer. And then, but throughout my year of life, I realized it isn't about where to go, but who to go with. So then I leave my question to my partner. And that is a fantastic idea, of course. Until the partner asks, why do you choose to be with me? And we're already in the restaurant. We sit down and have order. Now, this is a question that's more urgent than the previous question because you have to answer right away and you don't have too much chance to get messed up.
Sort of a Turing machine, bro.
So, but you have heard the first problem. So you should know what's a good answer and what's a bad answer. Let me show you a bad answer. And of course, it doesn't learn from my experience. An insufficient answer was because you have a great personality and an attractive voice. And the reason this is bad is because you are just saying she's a point on the solution set. Solution. So you're not saying anything, and you're just saying I choose it randomly. Okay, this is not very satisfying answer. So anyone can guess what's the right answer.
Because I love your social security number. It's unique.
Close.
If you're number theorist, that's a good answer.
I mean, right, because of implicit bias towards you, because the implicit bias, this extra measure determines a unique point usually. It's out of the whole solution. This is the precise. If your partner further asks, what does that even mean? You want to be precise, they want to answer. Precise answer. In the very beginning, remember at initialization, I already feel close to you. The measure is just that person. This is basically what the implicit bias thing do. Right? You have a solution set, you have a measure. The measure depends on initialization. You're destined to a point. And I'm not sure if this will work. So yes, but that's implicit bias.
I just want to make sure for my very naive understanding, you're not talking about training these models. You're just talking about going down in the gradient flow to the end state.
Yeah, but
That is-
that is the training.
That is.
Training equals gradient
Training
descent.
the-
Oh, okay, so the X and the Y are the training
X,
data.
Y is the training data, and W
Oh.
is the parameter you want to learn, right? So you learn your parameter and that satisfies it.
I'm so stupid, you can't even begin to talk to me, and now I get it. But I feel much closer to you now, in Wasserstein distance.
Okay.
Yeah, he's, okay.
Yeah,
That's also answer, right?
yeah, that's also my answer. That's my metric in Wasserstein. How much do I have to move to be approved? Yeah, too much, okay.
Okay, so let's start with part two. So part two is more top down. So we actually look at the full neural network and actually we do training and we try to understand what is going on. And for this, we really need a neurotangent kernel because it's describe a more macroscopic view of the training. So this is joint work with Roger, Gita, Maria, Donna from LU and Cal. So the model we consider is deep neural network. Again, you have a lot of activation bias set altogether, but the outermost layer is F1. Basically, you have some matrix and a bias, but in here, this H can have all sorts of complicated structure, like convolution, like dropout, like a lot of things. You train your parameters, so W is the parameter you want to learn, you train it basically. So very general model. And again, we train during using gradient flow or gradient descent just to minimize the loss and see. The loss we use is square loss. You can also use cross section. And let me fix a little notation. So in here, we're trying to do a classification problem. So X can be image or something or text. And then RC, so we have C classes. Okay, so it outputs a vector. And then if it's one in the first place, it's in class one. And usually it's not perfectly 1 and 0, but it's a probability of being class 1, etc. So XIC just means X, this data is in class C, the dog or this cat. And when you have bracket, that means you average over whole data among same class. So you average the nodes of all the dogs for average. And one thing people find out in empirically first, it's neural collapse, and this is first in Papillon. Why? This is one of the most celebrated paper. Basically, if you look at H, they call it feature because you can think about in the end you have your output, but your output is a linear combination of your feature. What they realized, so this is for picture, and from left to right is the time. So left is the beginning, and right is the end of training. So what you have is initially you have a lot of feature floating around and you try to train them, but eventually all the feature kind of collects to a single point for the same class, which is a little bit surprising because that means if you want to classify as a dog or a cat, it's sufficient to look at one particular feature. This feature might be a combination of ears and eyes and nose. But this doesn't always happen. And there's a big mathematical criteria. There's a four equality you have to set equal as new collapse. And this is great for compressed sensing because if you have all the feature collapse to a point, that means you don't need that many features anyway. You can just reduce the parameter of your network and you can compute things more efficiently. You don't have to.
So just, I like how your eyebrows go up when I raise my hand. Now here comes another question. Okay, so just so I understand, you're showing me these dots on the screen.
Yeah.
These represent the structure inside of the W. The amount of active nodes inside of W that you're trying to train.
Yes.
And then this collapses, so these dots are somehow a low rank structure inside of W, and this is being compressed down to the very small structure. I just trying to assign meaning to these pictures.
Yes. So
Because I'm not clear, I understand.
So this H of, so all the blue points, each blue point
It's a
H of
feature.
xi.
ECFO, you have H.
Yeah, this is feature. And
Yeah.
then xi because you have a lot of dogs, a lot of cats.
Yeah.
So you have a lot of things. And those things will change over time because you're training the weight. Right. So your feature will be changing.
So this is, the dots are the other features which are receiving some sort of attention, whatever it is.
Yeah.
Okay, some weight, some sort of weight involved.
Yes.
Okay.
And then somehow, if you're in the same class, two blue points are in the same class, they become closer and closer and converge to 1 point. So all the dogs will have their feature kind of collapse to a point, which is maybe not what you would expect. And this doesn't happen more often than you expect. And then people say, oh, we should study this.
I see, I understand.
And so, yeah, this means you can compress extensively on this model. And this is, again, very good because people also think about let's say if they teach a neural network, they bring the trained model into your laptop or your cell phone. And that requires that trained model cannot be too big. Like during the training can be big, but after training, if it's compressible, then you can put on your small device. Otherwise, you always have to connect to the cloud and then to do that computation. So this is also relevant in the application. But so far, everyone has an idea is that okay, if I see neural collapse, I can say it's neural collapse, but no one knows when it will happen. No one knows why it happens. So the work we did is, okay, neural collapse usually happen in the very end of training. Can we say something because we can see the whole training process? Can we say at some point that we can already predict in the end will happen? Then we already can, prepare ourselves for that. Just like when the implicit bias works, in the end, you can see a solution, but maybe in the beginning, we can already predict what the solution should look like. And here we want to say, is there a condition we can look at? We can say, neural collapse will happen or not. And actually we can. So this is very exciting. And the tool we use is neural tangent kernel. A neural tangent kernel basically is defined as the follow. It's a correlation between the gradient function. So not the correlation between function, but correlation between the gradient function. Meaning, if I train myself on the image of a dog, does that affect my training on the image of a cat? And then here, because the output is a vector, the input is a vector, this is like fourth order tensor. So that's why I will write a lot of indices because you have AX, IJ. Actually, if your X is complicated, it can be 6 order. But it's basically measuring the correlation. And this is something you can compute physically because it's just in a problem. We'll just give you data and compute easy. So NTK, I know either people love it or hate it because the original NTK paper in 2018, they discuss infinite width limit, and they have certain scaling. But what they come to conclusion is that neural network is basically a kernel. And this kernel is determined by your initialization, which is not interesting in practical point of view because why don't I just use kernel? I just need to find a good kernel. I never need to use neural network. But the reality is, if you look at the kernel in neural network when you train, the kernel changes a lot. They're learning how to measure the right correlation. And then, but it's very complex. That's why people usually don't analyze the finite one. They want the infinite width. But here we analyze the finite width because we want to, because we think it's very relevant to understand the finite case. And before we even do some theory, we do some experiment. And this is the kernel, what it looks like. Of course, this is slice because tensor. So apparently this structure is not a random matrix, I would say. You look at it, and fits this definition of local elasticity. Again, meaning that if you train yourself learning information of dog, this should not affect too much of your training based on information of a cat. Basically, if you're across the class, and this is translated into the block structure, that kind of happen one-to-one. So based on the empirical study, we say, okay, let's make an assumption, and this is a definition. We say that the kernel has a block structure if it only consists of 3 kinds of correlation. One is the correlation of image with itself. So this is the strongest. The second correlation is image with another image, but in the same place. And the weaker one is an image with another image in different place. So it's reasonable to say lambda 1 bigger than lambda 3. But of course, this means that there are only three kinds of block. In reality, we might have a little bit more, but this is a reasonable assumption based on. And our assumption is the outermost neurotangent kernel block structure. By the way, we don't even need to know lambda 1, lambda 2, lambda 3. We just need to know it has this. And we assume the last layer, the feature space also has. Once you have that, you will get two things. One thing is that during the training, so training is the minimization of the loss function, you can break into three phases, very clearly three phases. One is the global resistance, so global means the global error average. So not taking absolute value, but just the average of your final result. And among the class and among individual. So you have three very clear phases, and then we only analyze the last phases. So this guarantees that when we analyze the last phases, the global mean and the class mean doesn't change. So this helps us to analyze the dynamics more contractually. And then the second assumption, when you have this block structure on the feature space, you can derive, again, algebraically, just write down the equation and you take time derivative, you find one invariant. And this invariant, it doesn't come from our intuition, pure algebraic, just write down the equation, mess with it. And this invariant kind of tell you whether you will have neural collapse, which is very interesting. So
Can you explain this? Is there any intuition in this for you?
I don't have it yet. So that's one thing that I would really like to understand because
This came out of some regulation.
just some
So there could be other variants.
There could be other invariants. Actually, I recently read a paper that they claim they can tell you, if you give them a differential equation, they can tell you how many invariants. They don't know how to find it, but they can tell you what's the maximum number. Which I think is also very interesting.
Symmetries and variants.
Yeah. So the theorem is follow. We assume it has block structure, so theta H have block structure. We assume that the feature are centralized, meaning the mean is 0, and this is very mild because you can always move your data somewhere else to make the mean 0. This is actually a very mild condition. The third condition is very interesting. So the invariant last phase, and if the invariant is 0, then we say, okay, you're well, we don't even need to see. And actually, we only prove one side, but our experiment is actually if and only if. So if your invariant is not even close to 0, then usually you don't have to. But we couldn't prove that. It should not be easy to show. Yeah, so in short, we can predict neural collapse given we check the condition. And this will help compress things. So the summary of part 2 will be that, first based on empirical observation, because basically we don't know what such observation makes. So we just do numerics and then, it has block, so we assume block. And then we establish and we claim this is the first theoretical connection using neurotangent kernel to predict neural collapse. And then the method we use is we separate the training phases into 3 parts, and then we analyze the invariant in the rest. Yes.
So if you predict there's going to be neural collapse, what's the most intelligent way to adjust your network to take advantage of the fact it's going to happen there? What do you?
I would just say in the end, you can tell your boss, or I don't know your boss or anyone, that in the end,
It will be compressed.
yeah, it will be compressed.
It's not like you can sort of say, oh, this thing is going to have neural collapse, so I can shrink the network.
Yeah, no.
You can't pre-compress.
You cannot pre-compress. Actually, I think there are papers saying that even though in the end it's compressible, during training you can.
Okay.
Otherwise, you'll get something.
Okay.
So during training, it's important to have a lot of. In the end, it's not. Which is interesting. So there's a few future direction. I have a lot more to think of. So the implicit bias again, I only have just 1 or 2 nonlinear thing in my loss function. I want to add more, but the analysis doesn't carry through when you concatenate too much because the Bregman divergence itself still has some hidden convexity inside. And when you kind of concatenate convexity with nonlinear things break down. But my hope is I can concatenate this elementary thing to more and more. Because I want to learn new regularizations. I want to learn like a very weird polynomial that I can use for my optimization. And the result, everything I analyze is still gradient descent, gradient flow in the continuous analogy, but people do different other things. So in reality, people do stochastic gradient descent. So you add noise, you only take subsample. And this will be, in the continuous case, will be stochastic differential. And that should have different kind of limit for those will also be interesting. The weight normalization of natural acceleration, we only have result for a particular case, but we want to generalize into certain class of non-convex optimization, which we can say, oh, those also work, even though it's. Yeah, and I want to analyze neural tension kernel because the infinite will say NTK just doesn't change, and the experiment always change. And in our case, we can only analyze the last phase because that's where it kind of stabilizes. But we don't have understanding of the first. It will be interesting. We also plotted what happened there, how to see it in the right way. But this will be very interesting because learning neural tension kernel is basically machine is learning the feature, like what is the most important feature of this problem. And the rest is like but finding the feature arguably is one of the most important thing, and this will help with explainability too. Yeah, and yes, the invariant, I don't have good interpretation. I want to understand it more because if there's a good meaning or understanding of it, maybe it will happen somewhere else too. I can spot it and use it. And in general, this is a very general last direction. I want to construct, so you can make any assumption you want, and based on this assumption, you have theory. But I do believe that if our assumptions come a little bit from experiment or application, it would be nice to combine the theory and the practice, and not like, oh, I have beautiful theory, but never, this cannot ever apply in practice. For example, the NDK paper has so much citation, it receives so much, people know it a lot. But then in terms of implementation, actually, if you search, there's very limited because no one is connecting the theory to the actual application. So that's my talk, and thank you for your attention.
So I'll stop the recording here and open up the